So the unit that we're in, applications of the derivative, last year was the low point of the school year for all of the seniors. It was, you know why? No, you don't know why. We haven't even hit the part where they all fell apart. There are 6 big ideas that we are covering in this unit. Big idea number 1 is L'Hopital's rule. When do you get to use L'Hopital's rule? If you have an indeterminate form, our favorite indeterminate forms? 0 over 0. Infinity over infinity. L'Hopital's rule is your friend there. But however, there are other indeterminate forms besides infinity over infinity and 0 over 0 that you want to use L'Hopital, but L'Hopital's rule only works for the quotient of 2 functions. What are some of these other indeterminate forms? 0 times infinity, now you're frozen. Infinity minus infinity. Lewis, give me another one. Oh, she stole your answer, didn't she? Infinity times 0, infinity minus infinity. David? 0 to the power of infinity. 0 to the power of infinity, Palimon? 1 to the power of infinity, Carmen? Stole your answer, Aaron? Infinity to the power of 0, and I think there's one more. Stephen?
0 to the power of 0.
0 to the power of 0. These are all indeterminate forms. If you see any of these answers as like a limit answer, that's not the answer. You have to go do L'Hopital's rule. You're going to have to do some algebraic trickery. Okay, good. That was big idea number 1. Big idea number 2 involves the mean value theorem. The mean value theorem is a theorem about derivatives. There are 2 conditions, 2 very important conditions that you have to know. Palimon and Aaron, if side conversations could end, that'd be great. 2 important. You guys are like whispering to one another, or Palimon's whispering to the air.
I was giggling. He was apple.
Okay, thank you very much. Okay, back to the mean value theorem and 2 really important conditions. Those 2 important conditions, Lewis, what are they?
It has to be continuous and derivative.
I'm sorry.
Has to be
I know it's Monday at 8:51, but for God's sake, they're in calculus BC. The function has to be
continuous and differential.
Now this is where we get ourselves into trouble when we're not specific enough. Continuous on a closed interval. I want to see those bear claws, right? Closed interval. And differentiable? On an open interval. Palimon, if they could open towards one another instead of away from each other, that would be good. Okay. Continuous on a closed interval, differentiable on an open interval. What are you promised though? What's the thing that you're promised with the mean value theorem?
There's a point.
There's a C.
Where the slope of the secant line equals the slope of the tangent line.
There is a point C, and at this point C, the slope of the tangent line at this point C is equal to the slope of the secant line on the interval. We're okay? Now, one thing I didn't hear you say, I like what you said, I don't love what you said. She's like, there's a C. Somewhere there's a C. Shush. There's a C somewhere where the slope of the tangent line equals the slope of the secant line. David, what'd you guess?
The C is in between the interval.
C is inside the interval. It does not promise you anything about the mean value theorem. Now maybe David's advantage is the fact that he's looking straight, no, he's not, he's twirling his pen, at the mean value theorem poster, which is conveniently located right near I lay high expectations for you on tomorrow's take-home quiz.
No. He's just trying to throw in that there's a take-home quiz tomorrow.
Thank you, Celeste. You're so intuitive. Let me rewrite your letter of recommendation and include that adjective as well. All right, so we've got that. Tonight, if you are lacking a homework assignment or you have a homework assignment that you want to make corrections to, I will be here until 5 o'clock. Just grab what you need out of the folder and pass it around. Or do what Aaron did. We'll just leave it at that. At 5 o'clock, any homework assignment that has not been turned in, any homework assignment that has not been corrected, stays that grade forever. Aaron?
Can you just come and do homework?
Can you just come and do homework? Yes. Yes. All right. Lewis, we've already talked. Palimon, David, Aaron. Yep, those are just some boys I know. All right, tonight's homework is assignment for lesson 54. Now here's what you need to know. Out of problems 1, 2, and 3, I want you to choose 2 of them. Out of problems 4 and 5, choose 1 of them. And then choose number 6. It says challenge question. Okay, the choice, Aaron, is that you're going to choose to do it.
No, I ate a C.
Oh, you're A to C. Man, you're having all sorts of apple problems today. You should stay away from apples. Choose 2 out of 1, 2, and 3. Choose 1 out of 4 and 5. choose to do problem number 6. All right, so now we move on to like the next big idea. The big idea has just come fast and furious. Up until today, you've known about one kind of maximum, and that kind of maximum that you guys know is a relative max. And if I asked you to show me what a relative maximum looks like, what would you draw? I'm seeing half the story. Ah, there's the other half. You got, Lewis has the other half. Right? When I say relative max, people always think, oh, this kind, the smooth kind, the rounded kind, the differentiable kind. But there's two. Right? The non-differentiable kind. So you can have this kind, or you could have that kind. Oh, how awkward. I was supposed to start with minimum. I started with maximum. Please adjust your notes. Okay, in both of these cases, my function has a maximum at x equals c, okay? And if I wanted to prove that a function had a maximum, one way I could do this is I could say f of x makes a change. F of x makes a change from increasing to decreasing at x equals c. We're all totally comfortable with this? I'm talking about the function, the original function is making this change. Or I could talk about the derivative. What's the change in the derivative, everybody?
Negative to positive? Wait.
Oh gosh.
Wait.
Everybody,
No, positive to negative.
everybody is one student, and that one student is wrong. Relative maximum, f prime makes a change. What's the change, all the friends?
Positive to negative.
F prime makes a change from positive to negative at x equals c. This is a relative max. This is what we understand a relative max to be. This is how we prove a function has a relative max. And I hope everybody's okay. Okay, relative minimum, well, that means that f of x must make a change from decreasing to increasing at x equals c, or we could say that f prime makes a change from negative to positive at x equals c. Is everybody like 100% okay? Total review, we've been here before, this is not new stuff. Now, here's the thing, some books will say relative max, other books will say local max. College Board tends to use relative max and relative min, but local max and local min are going to mean the same thing. What we're saying is that in a neighborhood around x equals c, that's the largest value. That's the highest point. That's what it means to be a local maximum. If I don't look everywhere, but if I just look around x equals c, it's the highest point, or it's the lowest point for a local. Everybody okay? It's time for some new flavors. Yep. There's such a thing as an absolute minimum. If you are the absolute minimum or the global minimum, it means you are the lowest point everywhere. If you looked across the land, if you looked everywhere there was to look, Andrew, you'd say, dang, this is the lowest point out there. Or absolute max, dang, this is the highest point out there. Now here's the thing. The function f has an absolute minimum at x equals c if f of c, if f of c is less than or equal to f of x for all values of x. We're not just saying in like a neighborhood surrounding c, but if I looked everywhere, this is the lowest point out there. So obviously for an absolute max, what we're saying is f of c is greater than or equal to f of x for all values of x. Now before anybody asks, infinity is not an absolute maximum. Why? Why are we not going to allow infinity to be an absolute maximum? Stephen, what you got?
It's not a real number.
It's not a real number. It doesn't make sense to say this number that doesn't even exist is the biggest number that's out there. That this is the highest point on the curve. It's not a point on the curve is approaching. Are we okay? David, you okay? Lewis?
Are we going to have infinity x value?
Oh, like heading off towards negative infinity? Absolutely. When we're talking about absolute minimum value, we're talking about the y value. If I say where does the absolute minimum occur, you're saying at this particular x value. So now let's see how much you guys really know. There are 5 different situations at the bottom. While I take attendance, I need you guys to come up with functions that satisfy these 5 different conditions. You don't need to give me a name for the function. You don't have to think of a parent function. You need to give me a sketch. So for example, I need a function that has a relative minimum, but that relative minimum is also the absolute minimum. Can anybody think of a function that you've seen that has a relative minimum that is also at the same time the absolute minimum? An absolute minimum that is also a relative minimum. If I just even think about parent functions, some examples come to mind. Let's get some hands on this one. What do we got? An absolute minimum that's also local. I see Lewis, I see Celeste, hoping for some new friends here, and a local minimum that's also an absolute minimum. Myra, what you got for me? Okay, the graph of y equals x squared. Is everybody okay with that?
Yeah.
Okay, this is a relative minimum. Somebody convince me that there's a relative minimum here. Why is this the relative minimum? Lewis, why is this relative minimum?
What's the only minimum? So it's like the lowest.
No. Listen to the adjective.
F.
Relative minimum. Why is there a relative minimum here?
Because f of x changes from decreasing to increasing.
Because f of x changes from decreasing to increasing. Now I need an argument for why it's the absolute minimum as well. Not named Lewis, somebody else. Why is this the absolute minimum? Don't overthink it. Why is this the absolute minimum, Pelham? Absolute minimum because this is the lowest point. All right. Everybody get this under control?
Yes.
You've got relative minimum, which is going to talk about like changes from decreasing to increasing, or derivative changes from negative to positive. And you've got absolute minimum, which is just going to be like, hey, it's the lowest point on the curve. All right, with that said, finish them off. 4, 7, 11.
The same one. It never changes from decreasing to increasing.
Oh, and absolute max.
Right, I'm not saying it's an absolute maximum and an absolute minimum at the same time. I'm looking for a function that has both.
Also, then this one will be here. Because that one.
I guess, yeah.
And this one.
I was
Because it doesn't have an absolute.
Oh, I didn't
minimum.
read
This is
that.
not absolute.
Function that has an absolute maximum.
They oscillate.
Oh,
Because they oscillate.
Oh, but it
The
has.
highest point is still the highest point.
what?
Which is and then asking if it's
That's the highest.
So it can't.
No, it doesn't. It will come back,
Okay.
it will hit the same.
And why would that?
minimum.
I agree. So the graph that's upside down has an absolute max. Where's the absolute max?
This one would be this.
The middle, the fancy word for that would be like the vertex. And there's no absolute minimum.
Okay.
because-
Okay,
Maybe
I'm
we
doing
can
it.
use closer.
Right, actually negative, right, because the graph is decreasing. So in that case, we'd say
Okay,
there is.
this graph, so,
How are we doing over
Yeah,
here?
that's, I know that. You just explained to me.
okay.
And don't overthink it too terribly much. You don't need parent functions. I don't even need the name of the function, just a sketch. Friends over here, how are you? Function is both an absolute maximum and an absolute minimum. So where are you saying there's an absolute maximum? Right there, and an absolute minimum. Love it.
Does not have an absolute.
Love it, love it, love it.
Yep. Must be old.
The opposite of X.
Then this one would be
Oh, the last one.
Oh,
Go
man.
around the right. By the way, so what you get from the last one?
An absolute maximum and an absolute minimum. Where would you say the absolute maximum?
It'll be the tones that,
Okay.
It'll just be in
because they don't have an absolute minimum. In
Now here's the thing I'm a little worried about.
It doesn't go like this.
If
You
you
just go like
if I'm going to put arrows on here and that graph's going to continue to increase, then this cannot be the absolute maximum.
That's what I was trying to say. When you do arrows like that, it's not absolute.
Right. This is the problem. Is now you're allowing the function to go on to infinity, and that becomes a problem.
So it just be
Oh,
like
this one is like this.
Yeah.
Wait,
Or this
I
one.
have an absolute.
Yeah, what did you put the last one?
What's it called? It's something.
No, the last one.
All right, let's see what Myra's got for us. And thank you very much. All right, situation number 2. I want a function that has shush, that has both an absolute maximum and an absolute minimum. What do we think about number 2?
Minus the arrows is good.
An absolute max and an absolute
Oh,
minimum?
they're dots, she changed them.
Yeah, they're good.
Okay. If you use arrows, we cannot let this work, because then what you're saying is this graph is going to continue up forever, this guy's going to continue down forever. If, however, she replaces them with dots, and you're like, okay, here's a function that doesn't go on forever, that's an absolute max, that's an absolute min. Okay? All right, number 3, a function which has an absolute max but no absolute minimum. Upside down parabola would work. A relative maximum which is not the absolute maximum. A relative max that isn't the absolute max. So I'm not 100% sure what you're telling me here, Myra. So this is a relative max. Oh, and you're saying because the graph does this thing, this guy is a relative max, but not an absolute max? And this guy is a relative max that is an absolute max? Okay, good. And last one, a function which does not have an absolute maximum and does not have an absolute minimum. The straight line. Works for me. Everybody okay with all the adjectives floating around right now? All right, perfect. Myra, take it back. Whoop. All right. One more thing that I want you guys to do is we're going to start looking at absolute max and absolute minimum, not over the entire number line, but on like a restricted domain. This is really going to propel us into all the work we're going to do with the extreme value theorem and some problems that are coming up. So what I want you to do, and this should be another quick thing for you guys to do on your own, take 3 minutes. For this particular function, for these given intervals, identify for me the relative maximum, the relative minimum, the absolute max, and the absolute minimum if they exist. Ideally, your answers are going to be written as points. I want an x coordinate and a y coordinate. Okay, 3 more minutes, see what you can do. Myra, that is 2 almost exactly matched all the ones I have. The examples that I did. I know. You're a good girl. It's I let you look at one. I have no doubt you would nest somebody else. Do you need some lifesavers? Do you need some lifesavers? Or a hug? You said you need booze?
I don't know.
No. I don't think you want to be.
You're welcome.
At -2.4 wouldn't the maximum be?
Right. So if you're putting your blinders on, you're like, hey, I'm only going to look from -2 to 4. Where's the absolute maximum?
Wait a minute.
4 comes in.
I thought that was the trick because yeah, it like slightly stops before 4. I was like, yeah, the trick because it stops like it goes 60 before it goes before.
I think I tricked you.
That's why I was confused. I was like, it doesn't.
Only got him.
That's not the same as, wow, that was meant to be tricky.
Well, like, it's not at 4. Like, how long did you like?
Friends back here, we're doing okay? This hopefully feels very comfortable. There's just some new adjectives in your life. We've got global, we've got. The thing to keep in mind though, if you're going to justify something like a relative max, you're going to talk to me about the change. A change from like graph goes from increasing to decreasing, derivative changes positive to negative. Absolute max, this is the highest point. Get out. All right, I don't know that there's much conversation we need to have about these, but here are my answers. Compare them to yours. Let me know if there's anything that we need to talk about or clarify. Clarify. When it, yeah.
Can there be more than one relative max and one minimum?
What do you guys think? Can a function have more than one relative max? Can a function have more than one relative max? Could there be a place where the function changes from increasing to decreasing more than once?
Yeah.
Yes.
Sine.
Sine graph does that. Perfect. Cosine does that. Lots of functions. Can there be more than one absolute max?
No.
There is a highest point on the graph, for sure. There can't be two of them. However, we're going to allow ties. Like there could be 2 points on the graph that are the absolute maximum. Right? If I said, what is the absolute maximum value, whatever the y value is at those particular points would win. If I say, where does the absolute maximum occur, it occurs at multiple places. Sine of x is another great example of this. Every time you have a relative max, it is also the absolute max. Everybody okay? So we've got some new definitions, new vocabulary, and here comes a new theorem. Aaron, in a loud, strong, proud voice, can you introduce us to the extreme value theorem?
If f is a continuous function on the closed interval a less than or equal to x, but x is less than or equal to b, then f must have an absolute or global maximum and an absolute global minimum on that interval.
Okay, if you have a continuous function on a closed interval, so think about continuous function, closed interval, the extreme value theorem says you always have a highest point, you always have a lowest point. How many guys, if you think about that, it just kind of makes sense? Right, think about any continuous function you would ever draw. Continuous function, closed interval. Whatever you're envisioning in your head, can you see the highest point? Can you see the lowest point? So this should hopefully just kind of like intuitively make sense. All right, I need 2 actors, 2 thespians that would be willing to come on up for this next piece. David is down. I've got 1 thespian. I need 1 more.
Sure, I'll do it, man.
And Aaron. All right, David, pretty in pink. You are the wise wizard.
No, I want to be the wise wizard.
Too bad. And Aaron, you are the mighty maverick. Come on up in front of the camera. Bring your packet so that you can get your lines. Get up here. All right, Stephen, make sure you get our 2 thespians over here.
Wait, who am I? Shake my.
All right, we got a wise wizard, we got a mighty maverick. There you go. Wise wizard, you ready to start?
Yeah.
Go for it.
Okay, I get it. There's an absolute extrema and relative extrema. But what's the big deal?
Well, I was chatting with Mr. D last night, and he said that a lot of the problems we're going to study in the coming weeks will involve domain restrictions.
And I care why?
Well, with these domain restrictions, we always need to check the endpoints. Sometimes the relative maximum or minimum points won't even be in the interval we are restricted to.
Alright, I'll be sure to check the endpoint. After all, I do want to do well on the AP exam.
That's the spirit.
Hey, I noticed that I noticed that the extreme value theorem said the function has to be continuous on a closed interval. Do you think it makes a difference if the interval was open or half open?
I have no idea. Let's ask Mr. D. He knows some math stuff.
No, that's not the line. That's not the line. All right. First of all, thank you very much. 2 claps on 2 for our thespians. 1, 2. Okay, the extreme value theorem is about a continuous function on a closed interval. You have to have both conditions. And I realize, like with all your smarticle particles, we just kind of are at the point, like, yes, these conditions must be true. But for example, think about the graph of 1 over x on the interval -1, 1. Is that going to have an absolute max and an absolute min? Y equals 1 over x. From, call this -1, call this over here, x equals +1. Is there an absolute maximum?
No.
Oh, that was awkward. Nope. Is there an absolute max? If you look on the interval -1 to 1, is there an absolute max? If there is an absolute max, where is it? Wherever like this is.
Yeah. No.
No, is that an arrow? No, that's
Oh,
not.
okay.
The graph of 1 over x has that vertical asymptote over here at x equals 0.
Yeah.
Where's the absolute max?
There
Said
is
another
no-
way, where's the highest point?
There is.
There is no highest point because we know this graph just continues increasing forever and this guy continues decreasing forever. So if I were to remove the condition of continuity, I'm allowing asymptotes to show up in this problem, and this guy is not going to have an absolute max and it's not going to have an absolute minimum. Are we okay?
Mm-hmm.
All right, and what about like a half open interval? For example, if I continue to look at the graph of y equals 1 over x, here's the graph of y equals 1 over x. Ooh, I did not mean to cross the x-axis there. And I'm on the interval x equals 1/2 to infinity. So this is like a half open interval. I'm including the 1/2 and I get to go out towards infinity. Is there an absolute max?
Yep.
For sure. Polynomial is the absolute max.
I won't have.
And x equals 1/2. This guy right over here, I think the coordinates are going to be like 1/2, 2. That is the absolute max. And Aaron, what do you think about the absolute minimum here?
Absolute minimum.
Is there an absolute minimum for this graph?
Yeah.
Why not?
Because the absolute minimum would be it's not a
Actually not true.
Well,
Not for
no,
the graph
I
of
mean
1
not
over x.
infinity, but
Think about that graph of 1 over x. What does it do? It approaches 0. Approaches. Does it get to 0? So there is no point on the graph where the y value is equal to 0? We're okay? So we've got intermediate value theorem, which is about a continuous function on a closed interval. You've got the mean value theorem, which is about a continuous function on a closed interval, differentiable on an open. And now you've got the EVT, which is about a continuous function on a closed interval. Okay, this idea of absolute max and absolute min is going to be really important to us for the next couple of days. Let's see what we can do with this first one. Oh my God, I'm so excited. So excited. I may not have actually provided you all with enough room on this first model problem.
This is the most room you've ever given us.
I know, and it may not be enough.
Okay.
All right. So let's have some conversation. Determine the absolute maximum and minimum values of the function f of x equals x minus 4 square roots of x plus 1 on the interval -1, 8. My question to you all, and I want you to have some conversation about this, does there have to be an absolute maximum and an absolute minimum? If so, I need to be convinced. Don't talk to me, talk to somebody near you.
Because
Does there have to be an absolute max and an absolute minimum? How many guys would say yes, there absolutely must be an absolute max and an absolute min? I see 1, 2, 3, 4, 5, 6, maybe 7. How many guys really have no idea if there has to be an absolute max or an absolute min? Be honest. Thank you for the honesty. Okay. The extreme value theorem says that if your function is continuous on a closed interval, there must be a max, an absolute max, and there must be an absolute min. So my first question, do we have a continuous function? Look at that function. F of x equals x minus 4 square roots of x plus 1. Do we have any denominators?
no.
Right? Do we have any places where we might have a vertical asymptote or a hole, anything like that? Giselle, you okay? Okay, so f is continuous. So that's enough?
No,
Why not?
you have to prove continuity.
Well,
No, you don't.
no, we're just gonna, at this point we're just going to say we know it's a continuous function.
Yeah.
But that's not enough because
See if the interval is closed.
you have a closed interval. So what I know is f is continuous on a closed interval. So what? What theorem am I going to use? The EVT applies, which means there has to be an absolute max. Yep, an absolute max and an absolute min. Not so sure what's happening with the handwriting this morning. Apologies. But you've got a continuous function on a closed interval. EVT applies. There has to be an absolute max. There has to be an absolute min. Now here's the thing that can be a problem. Where does the absolute maximum occur? There's really only 2 places. If I think about any continuous function, I don't even know what this graph looks like. But I'm just going to sketch something and be like, la la la, it looks something like that. If this is my interval over here, from -1 to 8, there's only a couple of places I would ever look for an absolute max.
Wait,
This is not what the graph looks like. This is just some like random beta
That is a
graph.
trick function.
Okay? I've got a closed interval, I've got a continuous function. If I'm looking for an absolute max, where I'm going to look, I'm going to first look at my relative maximum, and then the other place that I'm going to look, endpoints. You always look at your relative maximum and endpoints. Mr. Olympia, what can we do for you? Yep. All right. So step 1, let's go for relative max. You guys know how to find a relative max, right? What are we going to do? Relative max. How do I find a relative max? I look for where the function goes from increasing to decreasing, or where the derivative goes from positive to negative. So let's look for where f prime makes a change from positive to negative. I bet most of you guys are going to be okay with that. f prime is going to be 1 minus 4, 1 over 2 square roots of x plus 1. That's my derivative. That's my derivative. The reason that I found the derivative is I'm interested to see where does the derivative make a change from positive to negative. If the derivative is going to make a change from positive to negative, I'm going to figure out first where's the derivative equal to 0. So we're going to set that equal to 0. And now we're going to solve this. I need some clever algebraic thinking here. Lots of ways we could do this. Aaron, what's one idea? What do you mean plug in?
See, like, so you can say that what would get the denominator is equal to.
Oh, I see what you're doing.
Yeah.
You're kind of looking, all right, so you're saying if the denominator is equal to 2, what happens?
That has to equal, the whole number on the right has to equal 1 minus 1.
So if the denominator is equal to 2, then you get 2 over 2, which is 1. 1 minus 1 is going to be 0. So you're kind of isolating this part and saying, what would it take to make this part equal to 2? And then you plug, nice. Did anybody else think of it that way? Okay, me neither, but totally inspiring. Okay, the other way. Let's do some algebra. We're going to get to 3. Lewis, what's your idea here?
Minus 1.
Okay, minus 1. So if you do that, you're going to say negative 2 over the square root of x plus 1 equals negative 1. Need more algebra.
Times square root of x plus 1.
Okay, like back in high school when I was in the gangs, they used to call me fraction killer. Because whenever I was solving an equation that had fractions, I would kill off the fractions by multiplying by the common denominator. Carmen's wondering what kind of gang this was. What I know is that negative...
It's called math club.
Yeah, there you go. Negative 2 over square root of x plus 1 times square root of x plus 1 is negative 2 equals negative 1 times the square root of x plus 1. I know, and now what do we get? Hey, we get to 2 equals the square root of x plus 1. The thing, Aaron, that you kind of intuitively picked up in the beginning. You're like, the square root of x plus 1 has to be equal to 2. Now what? Square both sides. Solve it for x. X is going to be 3, the same 3 that Aaron had like 14 minutes ago. Is everybody okay with getting to 3? This guy here is what I'm going to call my candidate. This is where I might have an absolute maximum. But I want to be careful though. I want to be really careful. We don't know right now if this is a relative max or a relative minimum. If you want to figure that out, it's been a while. You're going to need to do a number line test. At x equals 3, the derivative is equal to 0. Your job is to figure out what's happening around 3. Let's see, around 3. Pick something like to the left of 3 that wouldn't be horrible to work with, like 2. And now you got to be careful. Where you plug in the 2 is really important. You want to plug it into the derivative before you started solving and moving things around. So you want to come back here and think, okay, what's going to happen? If I picked x equals 2, if I plug in 2, we're going to get 1 minus 2 over the square root of 2 plus 1. 2 plus 1 is 3. Square root of 3.
2 over 3 over 3. It's going to be negative.
It's going to be negative.
What do we know for sure about square root of 3? It's between what two numbers? Square root of 3. Between 1 and 2. Take the number 2 and divide it by some number between 1 and 2. 2 divided by some number between 1 and 2. Now here's the thing. What I'm hearing is positive, but positive is not going to be good enough here.
It's greater than 1.
Because 1 minus a positive could be positive or it could be negative. What I really need to know is how does this compare to the number 1? 2 plus 1 is 3. Square root of 3 is between 1 and 2. 2 divided by some number between 1 and 2 has to be greater than 1. So 1 minus greater than 1 would be negative. Okay, I heard Aaron say, why didn't we just pick something nicer? Something nicer like 0. Had we picked 0, which is still to the left of 3, you'd have 1 minus 2 over the square root of 0 plus 1. 0 plus 1 is 1. 2 divided by 1 is 2. We're going to get a negative number. So let's pick something smart to the right of 3. 8. Polynomial why is 8 a good number?
Because you just add 1, 9, square root of 9 is 3.
1 minus 2 over the square root of 8 plus 1. 8 plus 1 is 9. Square root of 9 is 3. 1 minus 2/3 has to be positive. So what do we know about x equals 3? Relative minimum. Because f prime changes from negative to positive. Not the end of the story. Because what I think we've forgotten about is what were we actually trying to find in the first place? You wish. Relative max and min. Absolute max and min. Okay, what we know is that my graph has a relative minimum at x equals 3, but we don't know about is this the lowest point? So here's the thing. Once you find your derivative, then you figure out your candidate. What we're going to do is we're going to evaluate f at candidate and the endpoints. Because what we know is this. There's only one place where the derivative is equal to 0. There's only one place where I have a relative extrema. What I need to do is evaluate the function f at -1. I'm going to evaluate f at 3, and I'm going to evaluate f at 8. We're going to evaluate the function at the candidate and at the endpoints. F of -1, well, what is that? That's going to be -1 minus 4 times the square root of -1 plus 1. What is that? -1? F of 3 is 3 minus 4 times the square root of 3 plus 1. 3 plus 1 is 4. Square root of 4 is 2. I think that's what, -5. F of 8 is 8 minus 4. Square roots of 8 plus 1. 8 plus 1 is 9. Square root of 9 is 3. Times 4 is 12. -4. We have one relative extrema at x equals 3. We have 2 endpoints. We've tested the internal candidate. We've tested the endpoints. Where's the absolute max? Where's the absolute highest point on this interval? At x equals -1. So what I would say is that the absolute max at -1, -1, and I need an absolute minimum.
-3.
The absolute minimum happened at where?
-3, -5.
It happened at 3, -5. These absolute extrema problems are always going to be long. They just are. You're going to first start off by finding that derivative, set that derivative equal to 0 to figure out your candidates. Check your relative extrema. Once you've identified your relative extrema, then you're going to come back and you're going to evaluate the original function at the endpoints and at the candidate. With that said, you guys have 6 minutes. Show me what you can do with the next one. I've already done the hard one. You guys get this one. Everybody okay if I erase all the good stuff, okay?
Yes.
You weren't born. Okay. Okay.
Yes.
Are there more mutants like you back in the test tubes? Oh, there's a mistake again.
Because maximum is closed.
Yeah, so it's going to be back.
Oh, the curse continues.
Wait a
So
minute.
B6.
The curse of teenagers not reading carefully enough continues.
What we have.
Wait, so we have to take the derivative?
Yeah.
Yeah, so we can find I mean, B differential.
Because you're finding the maximum of the derivative. You have to use the derivative to find it of the first one, the normal one, right? So it's find to find the minimum or maximum of the derivative.
Shut up.
You have to use the derivative to find the minimum and maximum of the derivative.
And then,
So to find the maximum of the derivative, take two derivatives. Because you already have the first one, because
then we
that's
said
your
that
derivative.
we
So you treat it.
All right, most groups seem to have figured out what the mistake is. Polymer, what's the mistake that we want to avoid?
We're finding the maximum acceleration.
So if you're going to find maximum acceleration and I've given you velocity, what do you need to do?
You find
The derivative.
prime.
You're going to find, first of all, you're going to find one derivative, and I know this is like totally easy peasy, right? 3t squared minus 6t plus 12. This is what I'm trying to maximize, not velocity. So you have to actually start the problem here with this function. Okay, so here, find the absolute maximum. The absolute maximum on the interval 0, 3. And Carmen, can you convince me that this function has to have an absolute maximum on 0, 3?
Because A of t is continuous.
A of t is continuous
On the closed interval,
on this closed interval 0, 3, so what?
then UVT applies.
The EVT applies. And because the EVT applies, I'm going to have an absolute maximum. Does there have to be an absolute minimum?
Yeah.
You got to have both with the EVT. If you have continuous function closed interval, you get both. You get a highest point, you get a lowest point. Lewis, what's the face for?
Do you have to write A T or can you write B prime?
It's not B of t that I care about with the EVT, it's A of t.
But can you write B prime?
Or you could write B prime. Yep, I'll take that. All right, so for the sake of time, step 1, find those candidates. Candidates look like A prime of t equal to 0. How kind am I? I picked a nice function, 6t minus 6. That's going to be equal to 0 at 1. Is everybody okay with this being the candidate? Yeah. So if I look at A prime, what am I expecting here? Is this going to be a relative max or a relative min? Pick a point to the left of 1 like 0. You get a negative
Wait,
followed by, yeah.
we're doing A of t, don't you have to? We did bt squared divided 16.
No, so v of t is your original function.
Yeah.
I want the absolute maximum for acceleration. If this is what I'm trying to maximize, that's what I take the derivative of.
Oh, okay.
Okay? And so once you've got that, then the next part gets to evaluate. And be careful, you want to evaluate your acceleration at your candidate and at each endpoint. So go back to your acceleration. A of 1 is going to be 3 minus 6 plus 12, which I think is 9. A of 0 is 0 minus 0 plus 12. A of 3 is 3 times 3 squared minus 6 times 3 plus 12.
19.
21?
Wait.
Let's pretend it's 21. So what's the maximum acceleration attained by the cat? What's the maximum acceleration? There's two questions I can ask you here. What is the maximum acceleration? And when does the maximum acceleration occur?
The maximum acceleration is 21.
The maximum acceleration is 21. When does it happen? At t equals 3. Everybody good? Tonight's homework, you've got 4 problems. It's going to be good. I'm going to be here till 5 o'clock. You can use that time to work on the homework, or you can use that time to get corrections taken care of.
I'm gonna be a little late.
Don't be late.
I'm out with tomorrow. I want that to go back.